I'm Borozan, who's currently a scientific associate at the OICR in Vincent Ferretti's lab. Started in the physics world and then saw the light, came to biology, and he's going to tell us about some of the work he's been doing here at the OICR in our presentation with this nice long title. Ivan, take it away.
Thank you, Francis, and thanks. I would just like to thank the committee members for inviting me for this event. So I'm going to talk to you about a classification model for biological sequences that we have proposed not a long time ago, basically this year. And just to start, first of all, I would like to say that we humans are particularly good at certain tasks, such as grouping, organizing, classifying, learning by association. And these concepts have been extensively used through different branches of science, including mathematics, physics, chemistry, and biology. And it doesn't come as a surprise then, according to the Time magazine, the 31st most influential person in human history and the 5th most influential scientist is actually Carl von Linné, who is the father of the modern taxonomy. And below I just give you a graphical overview of different taxonomic ranks and levels, starting from the more general to the more specific. So today I'm going to talk about a problem in computational molecular biology, which is the correct classification of unknown biological sequences, having a database of sequences with known origin. So this is one of the fundamental concepts in biology, and sequence comparison plays a crucial role in phylogenetic and metagenomic analysis. A relatively recent arrival are next generation sequencing technologies, and they have dramatically accelerated the study of different genomes, including humans, microbial, viral, and other. So there are some challenges. I would separate them in two groups, technical and biological. So most next generation sequencing technologies produce short reads that present a great challenge for both phylogenetic classification and automated genome assemblies. Alignment-based methods are used. However, in some cases, they could lead to erroneous information when used with genomes that have undergone certain type of sequence arrangement that I'm going to talk about. And most of the classification methods use either the alignment-based or composition-based approaches, but not both, so they don't actually put them together. Biological challenge, we were particularly interested in sequence rearrangements such as genetic recombination and shuffling or horizontal gene transfer that are observed in a variety of organisms, including viruses and bacteria. So one way to classify a sequence, you would have, say, you sequence something and you don't know where the DNA is coming from, so you would blast it against the BLAST database, you would look at the hits that come on top, and you would then associate the label of that top hit, whether it's species or genus level, with your sequence. That's how typically it is done. However, BLAST can also give erroneous results because BLAST assumes a conservation of contiguity between homologous segments in the sequence. So if you have a query and reference, the blocks here are, say, these homologous segments. So if I now switch the blocks around, the BLAST would give a relatively low similarity score, and you would think, you would deduce that maybe these two sequences have nothing in common, although these two sequences can be actually very similar functionally. So we decided to propose a new model for sequence comparison and classification that would be applicable to both nucleotide and amino acid sequences, which will be biologically motivated, based on some mathematical principles, and it should improve the classification accuracy over purely alignment or composition-based sequence comparison approaches, and should improve the accuracy with which we could classify short reads coming directly, and raw reads coming directly from the sequencers without doing the assembly. So a small digression. So some of these measures we are using in our model are based on k-mers. So k-mer is a polymer of sequence of certain length k, and similarity measures based on k-mers, k-mer counts or frequencies are less sensitive to sequence rearrangement than the alignment-based methods. So I'm giving an example of two sequences, and I have switched them. And here we can see that if we count all the k-mers, there is only a difference of 2 k-mers between these two sequences. And the idea here is that these type of measures will be more robust to this type of sequence arrangement than the blast measure itself. So what are the sequences what are the similarity measures that we're using in our model? They can be separated into two, the alignment-free and the alignment-based ones. So the alignment-free, those that are based on k-mer counts, we're using the Euclidean distance. So basically, we count the k-mers in sequence X and sequence Y, and then this basically forms an Euclidean space, and we look at the distance between these two vectors in the Euclidean space, and we calculate the distance between these two sequences. So the choice of this metric is based on its simplicity, well-defined mathematical properties, and the fact that it was already used as an alternative to alignment-based methods. The next sequence similarity measure is based on information theory, and it calculates the difference in the average amount of information in sequence X relative to the sequence Y, and this measure has been already successfully used to reconstruct some of the phylogenies for whole genome sequences. The third alignment-free similarity measure is based on Kolmogorov complexity. It's a compression-based method, and we're looking at the difference in compression rates between sequence X and Y using a compression algorithm like LZMA. And the reason why we choose this similarity measure is because, first of all, we're expecting it to be to not be affected by sequence rearrangements. And second, it is complementary to the k-mer-based ones. It doesn't depend on either the k-mer or the k-mer counts. The other two measures we decided to incorporate in our model are the BLAST measure for DNA sequences and the Smith-Waterman for protein sequences. So the classification model, we have some assumption and certain properties. So first of all, alignment-free, alignment-based similarity measures are complementary in nature. So some would be better at classifying certain type of sequences than other. So you have to have a model that basically choose which similarity measure you would use for classifying a particular sequence, and this is done by we are proposing a combined sequence similarity score, which is basically a weighted mean of individual similarity scores, and this is how it looks like. It's a simple weighted mean, but the weights are basically determined by using the F-test statistics, and which reflects the discriminatory ability of each sequence, of each similarity measure to basically separate classes in the training set. So weights in this case are calculated adaptively and independently for each sequence in the test set. This is quite different from the existing model, since most of these models use weights that are, say, either constant or there's no weight because they're actually not combining anything. So we use the simplest possible classification method, which is the nearest neighbor method, and basically it assigns the class here shown in the picture is a triangle, which is the closest in distance to the query sequence. So it's the simplest possible classification model, which is also used as a benchmark when comparing to other more sophisticated models like the SVM. Okay, so this is a graphical illustration of what the model does. So say we have two sequences, M1 and M2, and we have a training set here. So we know that the training set belongs to the class circle, and M1 says, okay, this is a circle, and M2 says this is a triangle. If you combine them together, you will find that now the M1 measure basically compensates for the M2 because it brings this T closer to the true class. But if you're doing your weighting properly, that should actually bring this T even closer to its true class. So there is also, we have some free parameters in the model, very few. There is the k-mer size, which we vary between 2 and a upper threshold, which is indicated by log n. And this is basically to avoid classifying sequences based on their length instead of based on their content. So we've tested this model on 3 different data sets on viral sequences. So we have a training set of 800 viral sequences across 147 different genera, and we tried to basically determine the genomes for each of these sequences, viral sequences. We found that actual model is more accurate than most of the, if all of the state-of-the-art models out there. We've tested it also on metagenome data with 759 dp in length on average. And we were trying to predict the phylum, and we also found overall that actually it was better than the models we compared to. And we also used it to actually predict the family for protein sequences, and we have shown that a similar model that uses the compression-based measure with BLAST basically improved the accuracy by more than 13%. So in summary, we propose a model that combines sequence similarity scores to gain additional discriminatory information about sequences and to improve their classification. The proposed model is novel in that it uses an adaptive weighting scheme for each sequence in a test set, and it gives larger weights to similarity measures that have greater discriminatory weighting in training set. It improves classification accuracy over the current composition alignment-based methods. It works both on full-length genomes, reads from the real metagenome dataset, short reads, and protein sequences. And our model can be generalized to any number of similarity measures that you wish. And so on that, I'll just, we've published it in Bioinformatics in April. Well, the last version was published on April the 1st. And I would like to thank OICR, the PI I'm working with, Vincent Ferretti, and if you have any questions, I would be glad to answer.
Any questions for Ryan? Sure.
Hi, great talk. So I wonder how much does the accuracy of the algorithm depend on the training set? So you basically learn the weights from the training set and then apply, and then this is the weight. What if you had no training set and you have no adaptive weights? Will it still outperform all the other?
If you had no training set.
Yeah. So you would have equal weights to all the original.
Yeah. So that so there is one algorithm out there, FilmBL, that actually uses unweighted. It combines 2 measures using an unweighted scheme, and we basically improve upon the accuracy compared to that particular model.
The training set is something that's manually composed.
No, the training set are, we decided to download it. So these are all the sequences available from the NCBR FSeq. So there is nothing, I mean, of course, you could think that there is certain dependency on the training set. However, we tested on different training sets, and the accuracy was more or less the same. So when we're looking at viruses, bacteria, we found more or less always the same accuracy.